Thank you very much, Peter, for this introduction, and thank you all for coming. It's amazing to see so many friends mixed together with all colleagues, new colleagues. It's just, it's a bit overwhelming, yeah, I hope I'll live to the expectations. And of course, it's late in the evening, so this lecture will be very light. I also have a lot of my non-scientific friends in here, so we'll just keep it very low profile, and I'll even show you some pictures of when I was younger. So, without any ado, as Peter said, that's kind of been my career trajectory so far. And so one thing that you can distill from this is that I moved a lot. So I was born in Romania, in Bucharest, and after that, straight after university, I somehow, not quite sure how, ended up at the synchrotron in Daisy in Hamburg, and that was followed by a master at Rostock University, which is a very small city up north in Germany. When I moved there, it was still kind of early 2000s, so things were interesting, to say. There was still a lot of reminders of East Germany. After Rostock, I got a PhD position in Mainz, which is another small city in Germany. And then I moved to Dortmund. I'll tell you the story why. And after that, I finally moved to Berlin, which was my dream city, where I actually always wanted to end up, but it took me a while to get there. And since 2013, I'm here in London. So I just want to show you a little bit more details, because this is a talk about myself, so maybe share with you some things about my career path, which is probably not the most usual one, at least for a Royal Society lecture, but I'm very happy that things are changing and that, you know, you can be a little bit different and still get a Royal Society award. So, you know, I grew up in communist Romania. There wasn't much fun, and the fact that I had those funny pompons on my hair is not my fault. It was kind of compulsory. You couldn't go to school without them. And so, yeah, I was a child in like a very hard dictatorship. And, well, I didn't see a banana until I was 14, but that doesn't matter. It's not so important. And then things start changing, but it was a sense of general confusion when we went to university. And that is actually a picture in the lab. That's my friend Ivana. Ivana sits there in the back behind Mary. And so I guess that was at the end of the term when everything finished, and Ivana was sitting in the fuel cupboard, I think. And we were sitting on the benches, but it was all cleaned up. But yeah, university was confusing, and the 90s in Romania were a bit confusing, so I decided to run away. And the first opportunity that came, I took. As I said, I ended up at the synchrotron in Hamburg, very confused. I'm very young and very skinny by the look of it as well. And then from there, I got an offer for a master at Rostock University, which is actually not in chemistry, but in condensed physics. So I was pending between Daisy and Rostock, and I was doing, strangely, research on ferroelectrics and the characterization using a lot of X-ray diffractions. But that wasn't really my thing, so I then decided to get a PhD into something that was more chemistry-like. And so that brought me to Mainz. And that was an amazing research group. And I did have a lot of fun in Mainz. And there in the middle, I don't think I have a pointer. Or maybe I do. Yes, this is Klaus Unger, which was my first mentor. He wasn't my PhD supervisor officially, as I was working with his habilitant, but he was one of the persons that inspired me quite a lot. He unfortunately passed away last year, and I will always remember him. But because life is never so nice, my boss decided to actually get a real job, to become a professor, and he moved to the University of Dortmund. I'm sorry if there is anyone from Dortmund here, but I didn't quite like it very much. So I've decided to get out as soon as possible. So I got my PhD and moved to Berlin. And the reason I moved to Berlin, you know, people think that we're always driven by ambitions and career, but actually I moved to Berlin because I really wanted to live in that city. So it was first the city, and then, you know, what is good in research in Berlin. So this is how I ended up at the Max Planck Institute in Berlin. And I did live in Berlin 2005 to 2007. I did have a lot of fun. I did enjoy every bit of Berlin, including the techno parties. And, you know, people make fun of me because I always show this picture. This is the biggest techno club in Berlin. It's called Bergheim. It's probably the first time someone shows this in a Royal Society. It's also very special for me because that's where I met my partner. That was it, but I not only had fun, but also I worked very hard. I got my first independent position in 2007 as a group leader, and I started building slowly my group, and we kept growing and growing and growing, and it was fantastic until basically my contract finished. And in Germany, at the time, things are changing, but at the time, once you finish your habilitation, you basically need to look for a job. So habilitation only gives you the right to become a professor, so you will need to find a professorship. And somehow I found Queen Mary, and I've decided to move from Berlin, from a relatively large group, to Queen Mary, and I ended up with 2 PhD students from a large group, and nothing. So I had to really build it up from scratch. Funny story is that I moved to London in 2013, and although Romania was in the European Union since, I believe, 2006, it turned out we didn't have the right to work, only Romanians and Bulgarians. But on the application form, they only asked me if I was a member of the European Union. I said yes. And when I arrived, it turned out that I didn't have the right to work. So this is a secret. Well, it's not a secret because it's going to go on YouTube, but I was kind of working illegally for 6 months. And when I got my permit, one day after, Romanian and Bulgarians had full working rights. But, you know, with the current situation, this might become handy again, so I'm keeping it. And so, again, things start getting better, and I start rebuilding my group from scratch, graduating some PhD students, winning some awards, continuing to have fun with my group, going to conferences. Anna joined Queen Mary, which was a fantastic moment. Anna is sitting also kind of behind Omar. And she joined as a research fellow at Queen Mary, and we kind of joined our forces, and I'm very proud of her. She's doing amazing. And then we moved to Imperial, which seems like an easy thing, but it's not quite easy to take all this amount of people across from East London to West London. But luckily, the department was very welcoming, and they did everything they could to accommodate us. It was 2019, so things were normal, and so I integrated quite well. And then the pandemic came, and that's the picture of us in 2020 in Hyde Park. And just to make it very clear, we are not breaking any rules here. So I might have worked illegal for 6 months, but this was when the UK government said it's okay for unlimited number of people to meet in parks. They changed it after that, but we are fully legal. And so in terms of research, I did all sorts of things. It took me a while to realize what I want to do. I started with organic chemistry in my bachelor, and then, as I said, strangely, I worked for a while on ferroelectrics. And then I did my PhD on molecularly imprinted polymers, which is quite an interesting topic. It's some sort of a synthetic antibody. So you polymerize something around a biomolecule of interest, and then you extract the biomolecule, and you kind of get a as I said, a synthetic antibody. So my PhD involved a lot of chromatography, but I started working with porous materials. And from there, I moved into renewable energy storage and conversion. And I will tell you how I did that. So when I moved to Berlin as a postdoc, my job was using my chromatography background to convert biomass into useful chemicals like this, and then create some sort of molecularly imprinted polymers or some sort of a chromatographic column able to separate these molecules from each other. So what I started doing was hydrothermally treating biomass to get these chemicals. But every time I did that instead, I was getting this black precipitate at the bottom of my reactor. So rather than doing my job, I became very curious, and I started looking instead, what is this black precipitate that forms during this hydrothermal treatment? And it turned out that you got some really nice spherical particles. So this was kind of my path to glory, or the first glory, so to say, because I discovered a new way of converting biomass into carbon materials, a very low temperature in water. So a bit of a sol-gel process of carbon. In fact, what this process does, it mimics the natural formation of coal. Coal is formed in water with a bit of heat and a bit of pressure, but it takes nature 100 millions of years or more to do that. And I was able to do that in a few hours. And so I focused myself onto this rather than this, and I started understanding the structure of this material, and later, when I moved to the UK, looking for their application. Through this process, you also get another phase, which is in between the aqueous phase that contains these chemicals I was supposed to be working on, but I didn't. And I got also fascinated by this. These are the so-called carbon dots that are some nice fluorescent, complicated carbonaceous materials that have potential to be used along in photocatalysis, maybe not as photocatalysts themselves, but along with semiconductors to change band gap and things like this. So basically, that's how I got into carbon materials. And these are some structures that you make via this hydrothermal carbonization. And it's a nice, versatile technique because you could change morphology, porosity. You could do all sorts of nanostructures. You could basically tailor the structure of any carbon material you want in any shape you want. So it's a very versatile technique. You can also hybridize it with inorganics and get this beautiful nanostructure where you have carbon that is made from biomass with some nanoparticles in the middle. So here are some platinum nanoparticles onto carbon, and you could make a carbon holosphere, and if you really want, you can just put one single platinum nanoparticle in the middle of the spheres, and all sorts of other interesting nanostructure. These are some tin oxide carbon composites with mesoporosity. This is a lithium iron phosphate coated with carbon. All these materials are useful for batteries and things like this. Oops, something happened. There was supposed to be an NMR spectra there, but it's gone. I was just trying to say that not only I was doing all these beautiful morphologies, but in my past life I was also doing a lot of C13 NMR, trying to understand the structure of these materials. How do you go from biomass in water at 200 degrees to these spherical carbons, what they are, what the structure is formed. It turns out it's formed of all these furanic structures, and if you would have the NMR spectra, I could prove it, but somehow it's gone. So just to summarize, this was kind of a big thing for me, because once I've started talking about this hydrothermal carbonization, the world started taking up this technology. And it's nice to see how basically from when I started working on this up to now, endless groups have been taking up this technology and start using it to make carbon materials. And I know that we shouldn't be talking about H-indexes and citation, but this is not my own H-index. This is the H-index of the technique that I discovered, and it's very nice to see this. But today I didn't get this award for the discovery of hydrothermal carbonization. I actually got the award for the application of this type of materials in batteries and catalysis. So I want to talk a little bit about green bat and green cat, in case you've been wondering what that means. I'm just trying to, make it a little bit more fun. So, of course, I don't need to tell to anyone in this audience how important climate change is the biggest challenge we have, and this is basically what's going to happen if we don't do anything about it. It's predicted that by 2100, we're going to have 4.8 increase in temperature. So we all know that that's going to be the end. I hope everyone has seen the movie. Don't Look Up. I think it was a fantastic movie and speaks exactly about this problem. Luckily, we have a lot of policies in place, the Paris Agreement, of course, and also some more local UK net zero commitments. And now we want to keep the temperature no more than 1.5 degrees centigrade. And to do that, it's a big challenge. It's actually very complicated. And so I think the biggest challenge we have is how can we balance the energy cost and efficiency, so creating low cost and efficient sustainable technologies, but where will this energy of supply, where will our materials come from, so that we ensure that we have no carbon emission overall. So sustainability is just not only about building a sustainable technology, it's thinking across the box to what goes into that sustainable technology, what materials, what manufacturing processes, and how we put things together. So the UK path to net zero is to make actions across 4 important areas. And the first area is this blob here, which is purpley, and that's up to us. This will be small changes that we need to do in our daily life. For example, travel less. I guess we've learned that with the pandemic. We don't need to fly anywhere just for a half-an-hour meeting. Use less cars, shared mobility, cycle more, eat less meat and things like this, and also improve the efficiency in energy and resources. But the biggest of all of this is take up low carbon solution. And this is where the challenge is, and this is the area I'm also working on. So what can we do? And the big things for the UK is electrification. Everything will be electric, and so we need to increase the energy by quite a lot. And then hydrogen is another big factor in this scheme, and we'll tell you a bit about hydrogen today. And also as an intermediate solution, until we manage to build those sustainable technologies, until we manage to electrify everything, we can also do a bit of carbon capture and storage, but even better if we do carbon capture and utilization, meaning that we suck the CO2 from whatever is created. Eventually, we can also take it out of air once we got to net zero, but that's in the future, and then utilizing it to create sustainable chemicals and fuels. And then we just need to expand on these low carbon technologies once we develop them. And then the last thing here is the natural carbon storage, more forests, restoring peats and things like this. So as I said, one thing is clear, we're going to have a tremendous increase in electricity. The electricity demand could double by 2050, and most of the idea is that most of this electricity will be generating from renewables. So you see here, some is hydrogen, but most of it will come from renewable sources. And in the UK, these renewable sources, of course, wind. There's a lot of wind in the UK. And so this is a very complicated and confusing slide, and I made this on purpose to show you that it's very complicated, but also we have to be optimistic because we have so many options and so many technologies available. So I'll try to get you through this, but it's pretty much what I said. We're still using fossil fuels, or at least gas today. They emit CO2. We can capture this CO2. We can split water, and we can do this with electricity, with light, ideally, or via classical thermal catalysis. And from water, we can produce hydrogen. Once we have hydrogen and we capture this CO2, we can make a lot of good products, our most wanted chemicals and materials, but we could also make this directly from CO2 via electroreduction or photoreduction using just the protons from water, not the hydrogen, and getting to the same type of commodities. We could also electrochemically reduce nitrogen from air and create our future ammonia, which will be net zero, and we could use this as fertilizer for agriculture or for maritime transport. Once we have hydrogen, that'd be great, because maybe we'll see hydrogen planes in the future. I'm sure we will see. And definitely hydrogen goes into what is called a fuel cell, which can create electricity with only water byproduct, and these fuel cells will be able to power buildings and also heavy-duty vehicles and trains. And of course, let's not forget batteries. Batteries are an enabling, absolute crucial component of all this scenario, where they are able to store this intermittent renewable energy for the grid, but also for decarbonizing our transport in electrical cars. So now, of course, there's a lot of competing technologies here, but I think we need all of them, and we need to work on every single one of them to accelerate our path to net zero. Now, talking about batteries, of course, we all know what a lithium-ion battery, and I guess every one of you in this room has at least 2, if not 3, lithium-ion batteries at the moment with them. They're great, they're fantastic, they got a Nobel Prize in chemistry, they change our life, and we are very dependent on them. Now, for the non-scientific audience, a battery is a device that basically converts chemical energy, so energy that is contained in chemicals, directly into electric energy. And the way it does this is using some redox reaction, electrochemical oxidations and reduction. And the first one that discovered the first real battery is Alessandro Volta. He was a professor in Italy, I think at Pavia. He was on the Italian lira, but now we have euros, and probably was also the first professor that actually turned out to be useful for something. There have been many followed. So from this simple battery, which basically has a zinc rod and a copper rod emerged in a sulfuric acid or sodium sulfide solution, where zinc is given away electrons to copper, and then it generates electrons like this, we went to a lithium-ion battery, which works pretty much the same in the sense that we still have an anode that is graphite, we still have a cathode. There can be many, but traditionally, as discovered by John Goodenough, this was lithium cobalt oxide, and you have an electrolyte. And the way a battery works is that basically when you discharge it, so when you take electricity from your battery, you move lithium ions from the anode into cathode, and when you use your battery, when you use it to charge your laptop, the reaction is inverse. So the difference between this and the Volta battery is that this is chargeable. This is a secondary battery, whether the Volta battery, once you've oxidized all the zinc, the battery is dead. So this is the primary batteries that we normally throw away. Now, you may wonder what's in a lithium-ion battery. I said there's an anode and a cathode and an electrolyte, but actually things are very, very complicated. There's a lot of things in a battery. And because of this complexity, it's just so difficult to really improve these technologies and also find alternative technologies. So as I said, there is an anode, this is graphite, there is a cathode, let's say this is lithium cobalt oxide, and these are glued to current collectors, things that would conduct electrons. And the way they're glued is using a sort of a glue, which is called a binder. Sometimes you add something else that it's even more conductive to match the conductivity of these metal collectors and pass electrons through the anode and a cathode. And then in between, you have an electrolyte. The role of the electrolyte is to transport ions between anode and cathode, but not electrons, because they have to go on external circuit. The electrolyte itself is complex, and it contains organic solvents, sometimes 2 or 3, and a lithium salt that gives the lithium ions, and these salts can vary as well. There is a separator as well in between that the ions go through, and as you charge and discharge the battery, there's a lot of complicated processes happening. Your electrolyte, for example, decomposes on your anode, and it forms the so-called solid electrolyte interface, which is a messy organic layer. Lithium can plate on top of other dead lithium that is left on here on the anode and have these lithium dendrites. That's the reason why batteries sometimes explode, because the dendrites go through and pass through the separator. And also, the cathode can decompose as you have high voltages, and then you carry what's on the cathode on the anode that contributes to the interface formation, and it's in general complicated. That's why your batteries don't last very long. That's why sometimes they explode, and that's why they're still very unreliable. So our duty here is to make them better. Now, in a lithium-ion batteries, the anode stayed pretty much constant. We're still using graphite, but the cathode changed over time from the lithium cobalt oxide to the so-called NMC materials, and I've plotted here cost, safety, cycle life, power, and energy density, so you can compare this. So basically, this shows the capacity, so the higher this value is, the better, versus the potential. You want your cathode to operate at the highest potential possible. This is a challenge because most electrolytes are not stable at these potentials, and that's why ACI forms. But anyway, these are the material trends, and you would see that we're moving from the lithium cobalt oxide to more manganese and nickel-rich chemistries. And why we're doing this is that actually all the components that are in a lithium-ion batteries are on the list of critical materials according to the European Union. And that includes lithium itself. So lithium has been added on the list of critical materials in 2020, is the latest to be added on this list. And I told you cobalt, high up on the list of critical materials. And also graphite, it's on the list of critical materials. And many other things that you use in batteries, it's on this list of critical materials. And the way this is classified is economic importance. The more we use these metals, the more there'll be, versus the supply risk, meaning that there's not a lot of these materials. And I'll explain you a little bit. But what is clear is that the demand for battery manufacturing is increasing and increasing. And these are some predictions here. And you would see that by 2030, we would increase to 2,623 gigawatt hours. And most of this will be due to electric mobility, as you could see here, some of it for storage, but of course we will ban all the petrol cars very soon, and everyone will drive an electrical car. So there's a lot of pressure and demand on batteries. And as this demand increases, it's so our concerns about where are we going to get these materials for batteries. And so these are some other predictions from predictions of raw material demand in kilotons per annum on a base case, also by 2030. And you could see that all of it is going to increase by quite a lot. And that includes nickel itself, which at the moment is not on the list of critical materials, but as I said, we are moving from cobalt to more nickel-rich chemistries, and we might have a problem with nickel very soon. Also, the grade of nickel for batteries is nickel grade 1, which is quite important. Another problem with these materials is not that we don't have enough lithium in this world, is where is geographically located. And the easiest to mine lithium is from brines, and these are only located in South America, Bolivia, Argentina, and Chile. Cobalt is, as you might know, is all in the Democratic Republic of Congo. There are a lot of ethical issues against mining cobalt, child labor, and so on. And so is graphite. Most of it is in China, and so we don't have enough graphite in Europe. Well, there's some in Russia, but that's also complicated at the moment. So if you think of sustainability of lithium-ion batteries, it's not that lithium-ion batteries don't have CO2 emissions. If you look at this graph, you look at the CO2 emissions across the life cycle of a lithium-ion batteries, and these are in different countries, China, EU, and US, and you'd see most CO2 emissions come actually from manufacturing the materials for batteries and putting them together in a battery. And so in Europe, in 2018, for example, the CO2 emissions from lithium-ion battery production was about the same as Holland is emitting today. But the good news with lithium-ion batteries is that you mitigate the CO2 emission as you use your car. But that's only if your electricity comes from renewable sources. And that's where this difference comes between China, EU, and US, because EU and US has more renewable energy compared to China, which is pretty much based on coal. So the question, and I guess the holy grail of all battery research, is how can we address sustainability in batteries? How can we make that dream battery that is both performant, sustainable, and low cost? And this is a very challenging thing to do. And two of my amazing postdocs, Heather, who is here, I've seen her earlier, I don't know where she is, yeah, there, and Maria, who unfortunately can't be here because she had a bike accident. I wish she would be here. They've actually wrote an amazing essay on how we can diversify batteries beyond lithium, and it's, I think, still free if you're interested in reading it. And they also come with some sort of greener battery specifications of how we can make batteries greener. And so in my group, that's what my research is a lot about. How can we move beyond lithium-ion? How can we make other different battery technologies? And I'll tell you a little bit about these other battery technologies. I'll start with sodium-ion batteries. So sodium-ion batteries, they can be a very low-cost solution to replace, not replace because lithium will always exist, but coexist with lithium batteries. Why is sodium more appealing is because unlike lithium, that I said is very unevenly geographically distributed, sodium is all over, and in particular in Europe, we have lots of salt mines. The nice thing about sodium is, as I said, in a battery, you also need a current collector to put your anode and cathode. And for lithium, you have to use copper for the anode because lithium forms an alloy with aluminium, but sodium does not, so you can use aluminium on both sides, and so current collectors will be cheaper. And basically, they work exactly the same, or more or less the same, as a lithium-ion battery. So if you are a lithium-ion battery manufacturer, you won't have to change much. And there was a big announcement towards the end of last year with the biggest EV company, CATL from China, announced that they're going to launch a sodium-ion battery car in 2023, which would have slightly lower 160 watts hour per kilogram, I believe, with lithium on around 200 and above. But we'll be able to charge in 16 minutes. So this is very fast charging. This is the advantage, one of the advantages of sodium-ion batteries. As I said, a sodium-ion battery works very similar to a lithium-ion batteries. I showed you how a lithium battery works. Well, you also have an anode, a cathode, an electrolyte. This electrolyte has instead a sodium salt, and basically you shuffle sodium ions between the anode and a cathode, exactly as in a lithium-ion batteries. Now, the material trends in sodium-ion batteries, there's been quite a lot of work on cathodes, which is the positive electrode, and a lot of this work has been inspired by work on cathodes for lithium-ion batteries. The nice thing about the cathodes for sodium-ion batteries is that they don't use, in general, any critical materials. You could use things as iron and manganese, which makes them more sustainable by default. And there are more challenging about finding the right anode, and that's where my group is working on. And so, as I said, in a lithium-ion battery, you use graphite as the anode. But unfortunately, graphite cannot store sodium. And the reason is not necessarily that sodium is bigger than lithium, because potassium is even bigger and it happily goes into graphite. It's the interactions between the sodium and the energetics. With the graphite, it just doesn't quite fit. And so because of this, you need to find different materials to use as a anode in lithium-ion batteries. And graphite is a perfect type of carbon allotrope where basically you have a graphene. Everyone heard of graphene. There's a big boom in the UK, so there's many graphene layers on top of each other. If you don't have this perfect structure in graphite, and you have these graphene layers randomly oriented with each other, you can imagine it like a house of cards that you put them together, and then basically it's this situation here where you have a bigger distance between these graphene layers than in graphite, and you also have a lot of closed pores in between. Now, sodium happily goes into this type of material. And my group, we did quite a lot of research to really understand how we can maximize the amount of sodium that could go into such a disordered type of pseudographitic carbon. And we try to understand the mechanism of this. So coming back to my discovery during my postdoc, which was by accident, is hydrothermal carbonization, which turns biomass or biomass derivatives into carbon. Well, we did the same. We created this spherical carbon, and then we wanted to tune all the structures of this carbon, and I'll show you in a minute what I mean by tuning the different structures into these materials. So what I mean by tuning the structure is that, you know, in graphite, as I said, there's these graphene layers perfectly parallel to each other, and you have a distance of around, let's say, 3.4, or somewhere between 3.4 and 3.3 angstroms between them. Now, in these disordered carbons, you have different spacing between these graphene layers, and so we can tune this spacing between these graphene layers by tuning the different temperature at which you prepare these carbons, but also we can tune the pore diameters in between these graphene layers, and we also could play around with defects. So imagine this house of cards, or one card that could have some oxygen functionalities or other imperfection. This seems to be quite important for storing sodium. And if you look around, you would see that one situation performs the best, and this is when we have this particular interlayer spacing here, close to 3.7 angstrom, when we have a pore diameter around somewhere between 2 to 3 nanometers, and then we have a sweet spot for oxygen on these graphene layers. And so with the help of Chang, I saw she's here, and Emilia, she should also be here. Yes, she's sitting there near Heather. We've been doing some modeling, DFT modeling, to calculate the theoretical capacity if we would have oxygenated defects, and we saw that this would be different from our experimental, and also she modeled what would be the ideal interlayer spacing between these graphene layers for sodium to intercalate, and this seems to fit very well with our situation. So we've kind of concluded here that defects are important, but there is also some intercalation. And this is what happens at the first part of the sodium storage in carbon, which is called the sloping region. And then we wanted to understand the role of pores, because of course we thought the bigger pores we have, the more sodium can go in, and you plate it as metallic sodium. So with the help of Claire Gray and Chris, who's been wonderful, we did some solid-state NMR, and we've seen a peak for metallic sodium into these materials. but it seemed not to correlate really with the pore size, so we were wondering what's happening. Anyway, we did some more NMR, and we figured out there is actually no connection between the pore size of our carbon materials and the shift in this metallic peak, and it has to do more with the way sodium interacts with the aromatic structure of these carbon materials. And so, based on this, what we've concluded, with a lot of characterization, with a lot of electrochemistry, is that there is this sweet spot here where the interlayer spacing is large enough for sodium to go and sit as metallic sodium in these pores, and that's where we store more sodium. But actually, if we have larger pores, it doesn't mean that more sodium can go through, because the pathway to these pores is closed, because now the interlayer spacing between these graphite layers is too small, so the sodium can't get through the pores. And if we open up, so this is the same material, this material here that performs rubbish, basically there is no sodium storage, no plateau. Once we open up the pores, you see that you open up the capacity. So our theory seems to be right, and then my PhD student Hande has been proving further this theory, where she created carbons with the right interlayer spacing between these graphene layers and larger pores, and we could get to impressively high capacities. So what is happening is something, I'm a very bad drawer, but it's something like this. Sodium goes in, you need to have enough interlayer spacing for metallic sodium to go in. This storage here is very fast in the sloping region, and you can make this even faster by putting more oxygen or defects, so sodium can be fast charging batteries. And once it's in the pores, you can increase the capacity. And what you should actually avoid is having blocked sodium in the pores or too small interlayer spacing for the SEI formation. I'll skip this, but I told you that in batteries it's not only important to work on materials, but it's also important to understand the interface. And actually, the electrolyte, just by simply changing the sodium salt and the solvents, will give you a complete different interface. And this is not the interface you want. You want a nice interface like this. So basically, again, Emilia helped us do some simulations here. And we figure out that if you use the right electrolyte, which is an ether-based electrolyte, you get a very, very nice interface. And if you use a sodium perchlorate with a carbonate electrolyte, you get a terrible interface. So now you may wonder, what are sodium-ion batteries good for, and why do I bother so much? Well, sodium are going to be fantastic for the grid storage. They're very low cost compared to sodium, so they're going to store our intermittent renewables. They're great for short-distance mobility. There's a lot of these things in London today, e-bikes and e-scooters, low-speed EVs for city transportation, and I said they have the potential to be charging faster than lithium. So that was the story about sodium. I'm kind of running out of time, so I wanted to tell you a bit about, after I said that how we shouldn't be using lithium, I'm going to go back and tell you about lithium-sulfur batteries. But don't worry, I'm actually going to minimize the amount of lithium into these batteries, and that's what we're trying to do. So as I said, sodium batteries are great. They're low cost, but they're never going to be better than lithium ion batteries. But lithium-sulfur has the potential to be. So this is how much energy can be stored per kilogram versus how much energy can be stored per liter. So that means if you have a battery that is good here, you will be a very small battery that will act amazingly well. Now, lithium-sulfur battery work very different from this rocking chair configuration, lithium-ion, sodium-ion. There is more chemistry involved in here, in the sense that you oxidize lithium to lithium ions that go through the electrolyte and interact with the sulfur cathode, and what you want is this lithium 2S to be formed. And then you want this to revert back to sulfur and lithium. So this conversion is actually more complicated than it should be, so you don't, unfortunately, go directly to lithium-2S, but you go through a lot of these polysulfides, intermediates. Some of these polysulfides are actually soluble in your electrolyte, so they're going to plate back onto your lithium anode. You're going to lose your cathode. It's called the polysulfide shuttling. So lithium-sulfur have a lot of problems in the sense that their longevity is limited, and also you get a lot of dendrite formation on the metallic lithium anode, because now you use a piece of metallic lithium. So we have some funding. The only funding I have, I can complain now because I'm here giving a Kavli talk from the Faraday Institution, are these two amazing girls, Heather and Sam. And what they're trying to do is to make a self-standing lithium-sulfur battery. So we like biomass in our group, and we do all our carbon materials from biomass. Here, instead of using this hydrothermal process, I use something else that is more like a spider making fibers, and we use something from plants, which is called lignin. So plants have cellulose and lignin. Jason knows that. And hemicellulose. So the lignin is the one that gives structure to the plants. Anyway, we can extract, well, we can't extract it. Jason can extract it, and Aggie. Then you can use this lignin to create these carbon fibers. You make a fiber using some electrospinning by applying some potential, as I said, like a spider web, and then you carbonize to get a freestanding carbon mat. And so that's our technology for making freestanding lithium-sulfur batteries. So this is how our fibers look like. What Sam is trying to do is to understand if you can actually plate metallic lithium on these 3D current collectors in a way that rather than using a big chunk of metallic lithium, you use just a few lithium nuclei deposited on these carbon fibers, and that's your anode. And so you then prevent the dendrite formation and so on. We just started this work. Yeah, we're just looking how this lithium is plated on these carbon fibers, at which potential, if it goes, where it goes, it seems that it goes a lot on the separator, as I said at the beginning. But the idea is to have this carbon fiber mat with a bit of lithium nuclei, and to pair it with this cathode, which is the same carbon fiber, where Heather is trying to deposit directly lithium-2S8 onto these carbon fibers to make a cathode. And this cathode seems to be working very nice. Remember that before, for sodium-ion batteries, I told you the capacity was about 300. Now we can reach 1,000 milliamp hour per gram. This is normal for lithium-sulfur. And you could see how this lithium-2S is formed, and then it disappears again. So this seems promising, but again, we're really at the start. But the idea where we're trying to go with this is, can we make a structural battery? Can you imagine one day, since you get a very high energy density, an aeroplane made of or an aeroplane wing made of a lithium-sulfur battery, which is made of these carbon fibers that would be also able to store your electricity. And of course, if these carbon fibers are made from a biomass, it would be even better. But of course, this is a long-term dream, but would be nice. I told you a lot about batteries, but the last slide I promise I have on batteries is that if it wasn't complicated enough with lithium and sodium and lithium-sulfur, we have a potential to actually use really abundant metals, such as aluminium, magnesium, and calcium, where this would be the cathode, but then the anode, sorry. But the challenge is to discover a cathode that would be able to store these multivalent metals, which is very difficult because they're very highly polarizable. They interact strongly with pretty much everything. And so I have Anastasia that started to look at aluminium ion batteries, but we're not going to get into details there because things are very complicated. She has a hard job to do. Now, I was talking a lot about sustainability, but how do you actually quantify sustainability? Can you do it? And there is a method that is called life cycle assessment. And I'm not going to explain you what life cycle assessment is. I just want to show that there is a database. Depending on the material you use, that kind of tells you, how many trees have been cut, how much CO2 has been created to mine the material, what the processes has been done, and so on. The easiest is to quantify the global warming potential, but there are other factors you can quantify. And so we did this for one of our anode for sodium-ion batteries, but there is a way to do it. It's complicated and it's pretty inaccurate at the moment because those data are very variable. So quantifying sustainability is difficult. The very last minute I have left, I want to also tell you a bit about Green Cat, because I've told you a lot about Green Bat. And I'll be quick. I just want to show you how a hydrogen economy would work. As I said, batteries are important because they can store intermittent renewable energy. But so is hydrogen. And the scenario for hydrogen, well, we might have different colors of hydrogen. There's gray hydrogen, that's the bad hydrogen. That's the hydrogen that is produced from from gas reforming or coal reforming. It generates a lot of CO2. This is how most of our hydrogen is produced today. That's why it's highly unsustainable. And our chemical industry that relies heavily on hydrogen is so CO2 heavy. There's the option of blue hydrogen. That's doing exactly the same thing but capturing the CO2. There is now turquoise hydrogen, which means that instead of using gas to produce this hydrogen or coal, you use biomass, you do carbon capture and storage, and there is green hydrogen, and that's what our dream would be. And so the use for hydrogen is across all these areas. Hydrogen could be used in transportation and power, in fuel cells to create clean electricity, or to create alternative fuels. As I said, you could use hydrogen and CO2 to create alternative to the fuels we know today. You may have heard that there's big plans of replacing all the gas in our boilers with hydrogen and also heat pumps. You use hydrogen in industry to create chemicals and materials. You use hydrogen to reduce nitrogen to make fertilizers in agriculture. The plans for the UK is to go from currently 27 terawatt hour to 270 terawatt hour. That's a huge jump in hydrogen production. Most of it will be still by gas reforming with CO2 capture and storage immediately by 2035, and there will be some increasing green hydrogen via electrolysis. As I said, this is where hydrogen is going to be used. There is a UK hydrogen strategy, if you're interested in reading it. Ambition is to deliver 5 gigawatts production of green hydrogen, and this is where some blue and green hydrogen will be located around the UK, and it's about harvesting all the great power of wind we have in this country, and that's where the electricity will be produced to generate this green hydrogen. I stole this slide from Ivan without asking him, but I did ask him before, so it should be fine. I just wanted to tell you there's different technologies to produce green hydrogen, and it's all called electrolysis. The most trendy and the most efficient is this proton exchange membrane electrolysis. But basically what you do in an electrolysis is, again, you have a cathode and you have an anode. As in a battery, at an anode, you oxidize water to oxygen. This creates protons. It's moved to the cathode via proton conductive membrane, and here you have a catalyst and you generate hydrogen. This is a cross-section of an electrolyzer. So basically, you have here basically what I said, the membrane, and then you have your catalyst here that is good for producing hydrogen as the cathode, and then the anode is the complicated part, where you have an iridium oxide catalyst supported on a porous titanium, because this reaction is very corrosive and nothing is really stable. Now, the thing we should be worrying about is this oxygen evolution reaction happening here, so water oxidation. I'm not going to explain what an overpotential is, although there are many scientists here, so you all know, but it's basically the difference between the theoretical thermodynamic potential and the potential at which this reaction takes place. And as I said, for oxygen evolution reaction, this is quite high. That's why you need iridium oxide, which is a very expensive and critical material. And the titanium porous layer with the catalyst make the cost of green hydrogen very expensive. Now, what we're doing in our group, and in according to the UK government, is what if we make hydrogen but making something else useful at the same time? Because when you oxidize water, you create oxygen. It's not very useful. You use iridium oxide. So can we actually decarbonize across the sector? And that's where another of my amazing postdoc, Hui, is working, and she's working on biomass electrolysis. So rather than oxidizing water, you oxidize a biomass derivative, whatever it is, partially oxidize it to some very useful chemicals, and then it's easy to evolve hydrogen, as I said. And so what she did is she managed to actually produce green hydrogen and green plastic at the same time. So the way it works is she's using glycerol, which is a waste from biodiesel industry, and there's two paths to oxidizing glycerol, and we want to follow this path, which we want to make this molecule, doesn't matter how it's called. And once we make this molecule, we take some inspiration from homogeneous catalysis, and we use a Lewis acid step and a Bronsted acid catalyzed step. So we combine electrocatalysis with homogeneous catalysis, and we produce lactic acid. It's great to produce lactic acid. You may all heard of polylactic acid. You probably have all been annoyed with the biodegradable bags for our biodegradable waste, which melt before you take your garbage to the bin. So that's polylactic acid. Well, you could make it better than this. All the renewable cups and everything is made of this. It's a biodegradable plastic. So basically, we can make glycerol, a waste, to monomer to make biodegradable plastic and produce hydrogen at the same time. And not only that, but what we also do is we take PET. You all know PET from the Coca-Cola bottles and the Starbucks cups. What we do with PET, we ball mill it with some sodium hydroxide, and we can actually very nicely recover the monomer from which PET is made, which is terephthalic acid. So you could make a new PET bottle. So we could have a circular recycling of PET. And the side you make ethylene glycol. This molecule is actually quite similar to the glycerol molecule. So basically, what we do is we produce green hydrogen from this. So we can have a recycled PET and green hydrogen. So basically, we also work on production of green hydrogen with green plastic in one-step process. And I'm done. I just wanted to tell you that once we have this green hydrogen, we also work on fuel cells. And to confuse you enough, fuel cells, as I said, is that technology that uses hydrogen now to produce backwater and clean electricity. It's kind of the reverse of an electrolysis. Again, most popular is PEM, fuel cell. So here, once you have hydrogen, this hydrogen is oxidized to protons that are conducted by a membrane, an electron, that's your electricity. And then basically here you you have oxygen reduction at the cathode, which, as oxygen evolution in an electrolyzer, is highly inefficient, and you need a catalyst to lower this overpotential. Now, we all know that platinum is a critical material. As I said at the beginning, it's high up on the list of critical material. It's mostly located in South Africa. So what we do in our group is using the same type of carbon technology, but this time taking inspiration from enzyme to create this iron single sides coordinated to 4 nitrogen or 6 nitrogen supported on carbon. And the idea is to take inspiration from nature. My lobster disappeared for some reason. Oh, here it is. So we've been actually taking a lot of inspiration. Actually, we've been using wood. We've been actually using lobster waste which was very nice. That was back at the Max Planck, where we got the lobster for free. Omar. We've been also using pretty much of albumin, which is egg white and sugar, and we've also did a coral-like inspiration. So we're trying to make this catalyst very porous, and on them we support these enzyme-like materials. Jinju has been doing quite some nice work on this during his PhD. He graduated yesterday, officially, where he's been putting single sides. And basically, you see here, this is the platinum. Platinum is black, it works the best. What you need to look is this point here where you start getting some current and the amount of current. We're not quite as good as platinum, but very close. He's been also, with the help of Dan, who I see he's sitting there at UCL, been assemble a fuel cell, and it works quite nicely. And currently we're trying to optimize these materials with Angus and Jesus. They're trying, instead of one single iron, to put two iron close to each other and see how these two irons can influence the catalysis of this oxygen reduction reaction. There's a lot of intermediates involved, and that's what the catalyst does. It just breaks the linear relations between all these intermediates to get the minimum of potential and maximum current. So we're still working on this. And so fuel cells are great because you could, as I said, make cars with them. That's our famous Imperial hydrogen fuel car. You can make trains. There are already buses working on hydrogen all around London. And why not? Maybe in the future we will all fly a hydrogen-powered aeroplane. So I am now at the end of my talk, and of course the acknowledgement is the most important part. And I'm very grateful to have also worked with really amazing people. They have been doing everything, and basically this award is really for them, and not for me. That's why we're going to spend £1,000 maybe later on in the pub. I have a big group, so. And these are some pictures of a time, and you may have noticed that I always worked with a lot of women, a lot of wonderful women. And so I think it is true that having more women PI attract more amazing women scientists, and this is how we can fix the leaky pipeline. There's so many people I want to thank, and I'm sure I forgot some. In particular, the Imperial crowd. I didn't have more space for it, but yeah, I would like to thank Ivan, of course, for all his friendship and collaboration, Mary, James, Jenny. I don't know if Jenny's here. There she is, and I'm not sure if I'm allowed to say that, but she was my nominator for this award, so I'm very grateful for her. Thank you, Jenny. Nilay, my first head of the department, for being such an inspirational person. Omar, my current head of the department, for being such a wonderful head of the department, really wanting the best possible for our department. And the list is very long. I'm not going to read all of them. Of course, the Queen Mary crowd. I can see Joanna, Joe, and Petra here. They are amazing, and they're doing very well. The UCL crowd, Dan, Paul, and all the EIL, for being among the first ones to kind of introduce me to the UK academic family when I was here very lost. And James, that is also here. He was the only academic I knew when I moved to the UK, and he was an amazing mentor for me. And of course, everyone else, and Misha that I see here, I'm so happy you moved to King's, and I hope you're going to stay for a bit longer. Don't go anywhere. Claire, for all the NMR, Ludmila, Chang, the Birmingham crowd, Emma, Phoebe, and Zoe, my collaborators that are still in Berlin, Spain, China, Japan. I realize I don't actually work much with American people. Probably I should change that, or not. And of course, all the institutions I've been through, everyone that gave me their funding, and of course, my family, and my dad, who is no longer with me, but he would have been really proud of me today. He was a scientist himself. my partner, Renato, our first cat, and our adopted cat. And that's my new dog, my new dog that my mom got, and I'm kind of in love with the dog after 2 visits to Romania, so I thought I'll put him there as well. Her. Thank you very much, and I'm not sure if there are questions. Probably spoke too much already. Thank you.
Thank you very much, Magda. That was super, a great tour around a very extensive and very impressive body of work related to the topic. So we have time for some questions. Who would like to start us off with a question? I'm sure someone has something they really would like to ask after that really exciting, stimulating talk. Yes, I think we have a question here and then at the other side, and I'm going to pop down and grab this laptop, this iPad while you're doing that, because I know we have people online as well. So if you're using Slido online, you can put your questions by that format. Please go ahead.
Magda, a question sort of close to my heart in terms of recycling. I think you know that lots of effort going into battery recycling. If it works, and we do recycle lithium, for example, and the cobalt and so on, should we give up on the other metals and just stick with lithium?
No, I think it's important that we start recycling lithium and cobalt. Absolutely crucial, because it will take some time until we develop these emerging technologies. So it's a bit like parallel between should we still do CO2 capture or not. Yes, we should do it, but also in long term. But I think developing new technologies is equally important. But also these new technologies will need to be recycled at some point. So if we learn how to recycle lithium and cobalt and all these precious metals, we would then know what to do with the end of life of these new emerging batteries, because they also have to go somewhere, even if the economics are not so appealing. And I think with batteries, the recycling starts with putting things together better than they are currently today, manufacturing for disassembly.
Okay, we have a question over here and then one over on your right, my left.
That's all. It's absolutely fascinating. I just wonder, you hadn't really included anything about atomic energy, I thought. I don't know, maybe you did it right at the beginning in one of your diagrams, and how you see that fitting in. And also, as a complete non-scientist, does the amount of water that you use to make some of your hydrogen and so on, is that in conflict with the ever decreasing amount of water that's available for sustaining life?
Yeah, they're both very good points. On the first point of atomic energy, I'd rather not comment, because I am absolutely have zero expertise in this area. So I think, and that's my non-scientific personal opinion, that it's important to have some nuclear energy in the mix. But as you could see, the scenarios for the UK are mostly renewables. Other countries, such as Germany, are completely dropping nuclear energy. But again, this is really not at all my expertise, so I don't really have a scientific opinion. On the second one, with the water usage, yeah, you're absolutely right, and water is also a big problem. But as I said, there's this life cycle assessment, which you can actually quantify where the biggest environmental impact comes. A lot of time comes from the water utilization. And at least for my hydrothermal carbonization, where you use water to make this carbon, you can actually recycle the water. For water electrolysis, you could use water with desalination close to, sea water and things like this. But yeah. Electrolyzing something else than water is also very good.
Please.
Thank you very much, Magda. Wonderful talk. So first of all, I think it's a great testimony to saying that diversity and insights into many different countries and systems fosters excellence. I think your CV and the performance of your group bears credit to this. So thank you for this great introduction to not only your entire history and that of your group, but also to the matter. Now to the topic itself. The EU wants to decarbonize all relevant industries by 2030. This is the frame in which we will be operating. Yeah? Our industrial cooperator, VATA, wants to decarbonize pretty much even earlier. So how are we going to go about? I mean, one of the arguments being made here that you're weighing performance versus sustainability. I think the way forward should be really that we convince our industrial partners and the end consumers that green is not necessarily worse and more expensive. Green can be better. So, I mean, how do you see the way with this proposed technology to go into this particular direction, pricing in sustainability as a value-added thing? Thank you.
I mean, I see it. Please do convince the industry to do it. I don't know, it's just very complicated. All the big industries have made this commitment that they are going to reach net zero by 2050. Companies like Shell, BP, BASF. Are they actually going to do it by just giving a bit of money to universities to do something green? Well, I'm not sure. This is just very debatable, and that's something that I, again, don't have an answer. If there's any industrial person in the audience or some governmental person, they're best entitled to answer this. Yeah, it's easy to set goals, but how are we going to do it? Well, we shall see, I guess.
Okay, I've got a question online for you here. What about electropolymers used as electrodes or other applications within fuel cells? So I guess it's looking at sort of polymer-based electrodes.
I mean, maybe Jenny can answer this. And people that, I guess polymers are great, but conductive polymers are not actually that conductive. But again, I'm not an expert in polymers. I don't know, yeah. There is a possibility if you don't have 100 millions of steps doing the polymer to work well with a lot of solvents in between. If you can have that really easy to make polymer in one step, that'd be great.
Okay, any more questions from the floor? I have got another one here for you, but let's see if anyone else wants to ask anything out here first. Don't be shy, there are no stupid questions, remember? Oh well, not until Dan put his hand up. Sorry.
Thank you, Peter. Really enjoyed your back history. That was really, really entertaining. Thanks for that presentation. I know you've been very supportive of female scientists and young scientists, and lots of people here to show that. What advice would you give to someone setting out to do a PhD now in this kind of electrochemical, advanced materials kind of area?
Well, I guess start before the PhD, pick wisely. I haven't picked that wisely, but still I ended up okay. But it's better if you pick wisely. Make sure that this is really what you want to do, and that's the group you want to work. And while you start doing, I guess, just don't be afraid of, doing new discoveries, or if you come across something else that your boss might not agree, you should still try to do it. Get as many mentors as supervisor as possible so that you can talk with a lot of different people, and I don't know, be creative and proactive, and don't be shy. Just go for it. That's the advice I would give.
Okay, anyone want to ask a last question before we let Magda off the hook and better have a drink? No? Okay, well, let's thank her once again. And again, I would just like to take the opportunity to congratulate you on the award of the Kavli medal.
Thank you. Thank you.
Good. Thank you all very much.